That I want to
Okay, so let's start. Oh, hold it. We don't have any pictures. Okay. I'm hoping that it's just the projectors. So let me make an announcement and hope that the projectors are just warming up. If not, I'm not sure what I'm going to do. So I just wanted to let you folks know that we're looking for TAs for next term. So you should have gotten an email about that. I also made a Piazza posting about that. So if you're interested in TAing, the Piazza post gives you a link to how to go do that. And in particular, we're probably going to be looking for people for 317. So if you're enjoying this course and would like to TA it, submit an application. Don't worry too much about how you're doing, because if you're not doing well, we won't look at your application when it gets to that part anyway with respect to this course. So if you're unsure how you're going to do, but you think, hey, you know, if I do okay in this course, I'd be interested in doing it, go ahead and submit. We're also looking for stuff in our systems courses, so 313, 213. I don't know how many of you would have already, you've all taken 213, but you may not have taken 313, so those are other areas that we're looking for. So let me just try this all again. Okay. I'm not sure what to say. Pardon? Well, yeah, I said shut it down, and then it flashed, so I'm going to start it up again. Okay, so, oh, of course, now I've lost my microphone, too. Okay, stupid thing. Okay, so what I'll start with then is I'll have to describe to you what the slides look like and see whether or not how good my descriptive capabilities are. But of course, the first slide up is just sort of what we're going to talk about. So isolation and location, layering, and abstraction, sort of the big picture things. And then, when I turn the stupid thing off, it shuts the mic off as well. So I have to wait until it turns the projectors back on before I can get my microphone back. So it does say I can start now. It's even better than that. It comes up and it says, doesn't even give me the option to select projectors. Oh, here it's trying now. Okay, we'll see what happens. Okay. Oh. Now I have the microphone back, right? Okay. This is going to be like an absolutely joyous day if it keeps going like this. I will be joining the Ed Norris School of Technology disaster areas when it comes to this. Okay, so today our big theme today is network address translation and NATing, and maybe we'll go on to DNS, but kind of unlikely. Okay. So after today's lecture, that's not helping, but okay. I'm scared of whether I should try changing it to a different input here and then lose everything, because I could, of course, go to a Dropbox or something like that and try it. Whew. Okay, we've got it all. Okay, well, okay, so we're going to look at NATing today, and so given an IP header, you're supposed to explain its role, how it gets used in NATing, and then basically we're going to trace how that goes through there. And then I don't have up here, but we'll have something about talk a little bit about firewalls, because they also sort of fit in at this particular point. And if we have time, then we'll go to DNS. So first of all, though, are there any questions from last class? Okay, because the ideas behind connection multiplexing and that are going to prove helpful in understanding how NATing works. Okay, so here's a typical network. And as we've talked about, as we've sort of dealt with this so far, every one of those addresses on that 133.16.2 subnet are directly accessible from the internet. So if anyone out there tries to connect to one of those machines, they will be able to connect to that machine. Okay? So that's just the way that things are at the moment that we've been talking about. But there's another set of addresses, or a subset of addresses within the IP address space that are dedicated to private networks. So a private network is a network that isn't going to be connected to the internet. Well, of course, that's what everyone says, right? They always say, oh, no, we'll never connect that network to the internet. And then, of course, later on, they decide that they do want to connect that to the internet. But the interesting thing about an address or a network, if you're not going to connect it to the internet, then that means that if I have a network that's not going to be connected to the internet, and you have a network that's not going to be connected to the internet, then there's no reason why we can't use the same set of addresses within our own networks, right? We're not going to talk to each other, so we won't have any confusion. Everything just stays on our own little network, so everything should just be fine. So back all the way in 1996, this sort of goes back to Bob Kahn's stuff, right? So he was talking about the initial IP address spaces, and they knew that it wasn't going to be enough. And so back in 1996, they were already thinking about, well, how can we sort of delay when we run out of IPv4 addresses, even though back in 1996, they were already talking about IPv6. Okay? So one of the ideas was, well, if we have a lot of these private networks out there, if they use their own, what we'll do is we'll carve off some of the existing IP address space, and we'll tell people who, if you want IP addresses, but you're not going to be on the internet, then just use these. You don't have to apply for them or anything like that. You can just go ahead and use them. Okay? And if you've got a lot of people doing that, and they're not going to be connected to the internet, previously where they might have gone out and actually tried to acquire IP addresses, now they don't need to do that. And so hopefully you can double up, and that sort of puts off or lessens the demand on actual routable IP addresses, and hopefully pushes out when you'd have to worry about changing to IPv6. Okay? So there's the, so first thing is you do not have to memorize these addresses, okay? So you just have to know that there are addresses like this that exist. And if I ever care about an address being non-routable, I will explicitly say this address is non-routable. Okay, that's the term that I will use, or it's on a private network or something like that. I don't like to use the private network term because there are companies, for example, that will have networks and they'll say they're private, and what they mean by being private is not that they're not on the internet. It just means that you just can't go and hook up to them. Right? So for example, if you go on BC Ferries and you fire up your laptop or your phone, you'll often see a BC Ferries network there. There's one that you can actually connect to and get traffic on, and then there's another one that's just used within the ferry for stuff, and that would be a private network. And sometimes I think if you go to hospitals and things like that, you might also see these sorts of networks. You can't connect to them, but they're there, or they don't want you connecting to them. So they're private in that sense, but by the same token, they can still connect to the internet if they want, if they've got things set up properly. So I prefer not to use that term to avoid the confusion between the two, and typically will refer to these collections of addresses as non-routable. And the reason they're classed as non-routable, or another reason that you can think of them as non-routable as the appropriate term, is because if a router in the internet ever gets one of these addresses, it's free to just ignore it. Okay, so if it ever sees someone trying to send a packet to it, it can just drop it right away. It doesn't have to do anything with it. So, for example, on your home network, if you're sending a packet, say you type in an IP address, ping or something like that, and you go ping, and you put in one of those non-routable addresses, well, it'll probably go out your cable modem or your ADSL modem, and it will hit the first router of TELUS or Shaw, at which point it probably gets dropped. Okay, so those are the collections of addresses, and as you can see, there's a fair number of them. There's 16 million if you want a class. That's a class, just a 10 address. If you want 172, you can get 1 million. If you want smaller numbers, you can get 65,000. Doesn't matter which ones you choose. Doesn't. They're non-routable, right? So no big deal. And if you look at your home routers and things like that, often the addresses that you get will be of the form 192.168. That seems to be a fairly common one that they use for the home routers. Okay?
So if we're running out of IP addresses on this format, why are there so many of them that are unroutable?
Well, this is, because the idea would be that, okay, so this is going to take up, 17 million addresses out of 4 billion. But if let's just say, if UBC, for example, said that none of its addresses were going to be routable, and SFU did the same thing, and U of T did the same thing, we would free up more than one of those blocks because we can use them multiple times.
Definitely. But how many addresses could UBC possibly use? 17 million? It seems like a lot.
No, but a company could. And yeah, okay. So, and the last line actually sort of addresses that that idea in a moment. Okay, so we'll just, yep.
So these addresses are kind of like reserved keywords or reserved addresses, so that you never find these on the internet.
That's right. You'll never find. You should never find these out on the internet. So if you looked up someone's name or something, they better not return one of these addresses. Okay. So, okay. The very last line up there, which is a little difficult to see, okay, says in 2012 they added the network 100.64/10 for what was referred to as carrier NATs. Okay. So those of you, I'm not sure, I think it's Rogers that does it, that they actually NAT all of your phones. Okay, so if you go to your home router at home, like at Shaw and stuff like that, the address that you have on that router on your outside interface is an actual IP address that's routable, and if you looked it up, you could find it in a table someplace. Okay. But telephone carriers decided, or they thought, okay, well, in a place like Tokyo or someplace like that, I could have millions of customers out there. And what they want to kind of do is, a cell phone company is a great example of this. All right, so that if you look at someplace like a city, so there's our city, okay, it kind of looks like the cloud, right? And there's probably only like one spot in the city where the carrier would actually connect to the internet. They would have their cell towers and everything like that, and they'd probably all bring it back to that spot. And so now the question is, well, how many customers could you have in your city? So the number 4 million was picked, although that's probably these days too small. But if you go up to the next one, you could say, well, I could have 16 million customers, which is probably outside the scope of most companies for something like that. And then what that allows them to do, as we'll see, is it allows them to have one address on the internet, but 16 million customers that they can address. So now you really start to save things. Okay? So that's what natting is. I'll provide a more precise definition in a moment. But that's sort of the idea behind natting. We're going to do something like that. Okay? So here's the idea. We have our network set up. And on the bottom there are that 172.16.2/24, that's non-routable addresses, okay? So I never actually wrote that there. I actually wrote that with the right, a proper non-routable address, but we should really think about that. Okay, so that's a non-routable network there. Okay? But it's connected to a router. Okay, so it's connected to that router, and that router is connected to the internet. Okay? So because it's a non-routable address, if any of the machines on the inside there, so that's what I refer to as the machines that are on the edge there that have the non-routable address, I refer that to being on the inside, because it's sort of like the inside the room or inside the world, and then the outside is the rest of the wild, woolly internet. And that's sort of the terminology that I use. It's not official. Okay, so we're on the inside there, and we want to get out. So what would happen? Well, we want this to be transparent to the machines on the inside. So we're going to put all of the work make all of the responsibility for doing this onto the router. So this is your home router. Okay? This is the idea behind your home router. So it will be sitting there like that. It will have the interface that's connected to your cable modem or to your ADSL, or whatever it happens to be. It will have an IP address, assuming that they're not natting you as well, that is an actual routable IP address. Okay? So you can actually get to that machine. Okay? So now what happens is, suppose that your machine, say 187, sends a message to 189, or to the .23 up in the right-hand corner there. So it sends the packet out there. It just takes and constructs a packet. Right? So we'll have our destination IP address will be 189.26.51.23. And so this is our destination. And our source will be 172.16.2.187. Okay. So which piece of information is looked at to route this to the destination? Kind of gave it away, right? Used the word destination. So only this piece of information is used to route it to the destination. So the packet will, in fact, end up at 189.26.51.23. Okay. We'll end up there. And then what does it do? Well, if it's going to send a response, these things get flipped. So it goes to 172.16.2.187. .23. And now it fires that message out. And it hits a router. And it gets dropped. It says, it's non-routable. I'm not putting that anywhere on the internet. So it's gone. So nothing comes back. Okay. So just hold that idea for a moment. Okay. Now let's back up to the inside. Okay. So you'll notice, first of all, that on the inside, that if this machine wants to send a message to this machine or a packet to this machine, well, it would put that IP address on it. And when this machine responds, it would just respond with the source or the destination, the source IP, which is that one, and it would work. So internally, everything works. So it's only when we go outside that we've got a problem. So we somehow have to fix this problem. So what do we know? Well, we go, there's sort of internally what happens. And, oops, okay. So there's how we start out. So we're just interested in that piece of information at the moment. We take that. That's going to hit the router. And we know that on the router, if we back up, right, that this IP address here is routable. So the basic idea is, well, if that one's routable, when I hit the router, what I'll do is I'll replace, I being the router, will replace 172.16.2.129 with the IP address that the rest of the world sees and belongs to me. Okay? So I do that. Okay? So I get that there like that. So now the packet goes out there. It can get off to that machine. And if that machine sends a response, I'll get the response. The router will get the response. But it's not really for the router. Right? That packet really isn't meant for the router. That packet is, in fact, meant for one of the machines on the inside. So it's just not enough to rewrite the address. We're going to have to remember that we rewrote the address and where it came from.
Just for remembering destination. But just keep going.
No, keep.
Just like how would you remember?
Oh, you mean what does you need to remember?
No. How would you remember?
How me, the router, would remember. Okay. So I'll address that. Okay.
The 142.18, that's the external IP of the router, right?
Of the router, that's right. So remember that our router has actually, it's got two IP addresses, right? It's got this external one, plus it has this internal one. So the internal one we don't really care about, unless we actually want to talk to the router for some reason, right? If we're trying to get to the rest of the internet, we never use that address. It's only if we want to talk to the router. So that would be, for example, on your home router when you want to configure it. Okay, well, what IP address are you going to use when you configure it? Well, you're going to use this internal one, right? And that's partly a security feature in that, and then we'll talk about this when we talk about firewalls, but if you sort of say the only one that the only addresses that are allowed to connect to me to talk to that web interface or whatever have to also have source addresses on there, right? Then that means that someone can't come in from the outside and change it. So it sort of restricts it to the inside, hopefully, which is a little more trusted. We say a little more trusted, okay? Not completely trusted. Okay. So this brings up the next slide is, well, what else do we need to, oh, yep.
Sorry, can you go back a slide? So this, so you're saying that the router will replace the source. Oh, sorry, never mind. I figured it out.
Oh, okay.
So are we putting, so when the router picks up something from a private network, replaces the source with its own IP, does it put the private network's IP in the payload, or?
Oh, okay. So I think you're asking, I think, the same question that the fellow over here was asking is, okay, what do we have to remember, and where do we keep that information so that when the packet comes back to us, we can get it to where it goes? So one idea would be, well, what if we had a larger header and we put some information in the header or something like that? Okay, but there is no room for that. So what do? So here's sort of the idea. I'll draw out a picture here. Okay, so So here's our router. Machine A, machine B. Machine C, and machine D. Okay. And we'll just start out with that. And let's now sort of ask the question, okay, what information do we need to undo this? Okay, so let's start out by saying, okay, well, what information, the first thing I said was, well, let's replace the IP address, the source IP address with my own IP address, and then I'll go back. So if I look at it from that perspective, I'm going to send out a packet here. Let's say this one here. It's the source, destination. The source will be C. The destination will be A. And when I'm on the other side, the source will be the router, and the destination will still be A. And so coming back, the source will be A, the destination will be R. And to get this to C, we'll have to reverse this. So the source will have to be A still, but the destination needs to be C now. So essentially what we have to do is we have to change this field here. Right? That's the one we have to change on the way back. So we could start out by saying, OK, let's have a table. And what we'll do is we'll say, OK, here's the destination IP address. Let's say A. And here's the source IP address. C. Okay, so when the packet first goes out, I put an entry in here saying the destination is A, it came from C. And so now on the way back, when it gets to the router, I say, OK, where's it going to? You say, oh, it's going to A. OK, I must put in C. And so I put in C. OK.
So if D and C request A at the same time,
OK, so that's a very insightful observation is, well, what happens if they both went to A? Well, let's add this information in here. OK, so let's go to destination is A, but now it's D. Now we have a problem, right? Well, we only have a problem, actually, if what happens if we looked at the destination port? Well, if this were 80 and this were 55, we'd probably be OK. However, as we saw in our connection multiplexing, that's not the worst case. It's not going to be very good. OK, so it's going to be 80, which didn't help us. OK. So what piece of information could we use to distinguish the two? What would we do in connection? So now think of this from the connection multiplexing example and sort of say, well, what this really is we've got two things coming here into one, and we make them come from one, which is sort of the equivalent of firing up your browser on a machine and having two tabs. Right? So how did we distinguish those?
Port numbers.
Sorry?
Port numbers.
Port numbers, that's right. So what we'll do is we'll say, OK, well, let's put in the source port number. So we have our source port. Well, not quite. OK. So could C and D, wherever you're starting from, could they have chosen the same port? OK. So that's not enough, right? So what you have to do is you have to say, I'm running out of room in my table here. Oh, yep.
What if we had a buffer and just had an ID tag to each entry?
An ID tag for each entry?
So like, if there's something that looks the same, there would be tiebreakers, which would be just ID.
Well, but where are we going to get the ID from?
The router will assign it.
Oh, okay, I think you're doing what you're doing. I think what you're thinking about is a variant of what I'm about to propose, or what they do. Okay, so since this could in fact be the same source port, so far we've got nothing that's unique, right? Well, what we do is we say, okay, all of this stuff is the same. So what I'm going to do is I'm actually going to assign another port number. So I'm going to put out a different port number. So we're going to have, we'll call it the router's port number. So this table gets kind of messy. Okay. But ignore the bottom line for the moment. Okay? So suppose that machine C is the only machine active through the router. Okay? So start out with that. So what we'll do is we'll say, we'll record in our table the destination is A, it's going to port 80, the source IP is C, it came from 86. And then I have this other router port in here, and we're going to use that to break ties. But for the moment, we'll say, well, if no one else is using the router, right, there's no other traffic going through that, I'll just use 86. Okay? And so now, when I go out here, I've got my destination for 80, and my source is 86. And oops, did that wrong. Okay. We'll get it right yet. Okay. Okay, this is okay. Our source is 80, our destination is 86. So we come, yep.
When does the router know to close the open port for NATing?
Okay, we will wait on that. Hold that question, okay? Let's just solve the problem of getting the information back, and then we have the other problem is, well, this table is getting bigger and bigger and bigger. How do we make it smaller again? Okay, so that's another problem. Okay, so we do that, and so now the packet comes back, and we look at this and we say, who's the source? Okay, well, that was the router, or the destination was the router. It's going to 86, so it says, okay, gets into the router, it says 86. Looking at that port, where did it come from? It came from that destination, that port. Therefore, I have to send it back to C at 86. So in this particular case, the only thing I have to rewrite is the source address, making it back to C, or the destination, I should say, back to E. Now, the worst case scenario, of course, are always the most interesting ones. Okay, so we have the destination IP is A, port 80, source is D, uses 86. So we would look in our table and we would say, oh, everything's exactly the same, so I'm going to have a different router port. So I will put in here, let's say 860. Okay? Okay, and so now when the source is still going to be 80, but this is going to be 860. So we'll come back here and we'll say, okay, now I need to look this up, and we'll say, okay, router port came in at 860. The destination was me. The source was A and 80. Therefore, I send it back to D86. Okay. And if we sort of say, well, what? This isn't even actually the worst case, right? The worst case is, well, it's a variant of it. The source is C. But then we know that these ports can't be the same, right? So they're coming from the same machine, so this would have to be, say, 87. So whether it's the same port, whether it's coming from the same IP or the same port, the problem is essentially, we do the same sorts of lookups.
That's a good question. So if it's from, the source port's never the same ever like this?
The source, when they're on the same machine, the source port can't be the same.
Ever.
Ever. Well, I mean, within a time window, right? At the same time, right?
So if I make one request to go to Google, then I make another request to a search.
Yeah.
From the same application, the port number constantly changes for each platform.
Well, there's a duration associated with how long that connection is up. But if that connection is closed, yes, it'll change. And yeah, you go through these really fast. Okay.
What's stopping us taking all the 4 numbers together as a single identity, like a single ID? Then they'll never be the same. Like, so without adding like a router port number, we'll just take destination IP, destination port, source IP, and source port as a single like identification number. Then that will never be the same.
Well, it's true it will never be the same, but what do we do? But as soon as how do we make it unique on this side? Right? You're right in that it's never going to be the same on this side. But now we have this problem where we've only got the one destination IP address, or source IP address, depending upon what your perspective is. So we sort of, and as soon as we do that, one of the things that was distinguishing it, which was the source part here, is now we lose that piece of information. So, and it gets turned into the same thing.
We don't necessarily lose it. We can still kind of, as multiplexing, we can demultiplex it.
Right, but I mean, keep in mind, right, that if they're exactly the same, right, what changed? So you're right in that these things are unique. Okay?
But if the port number is the same, then the source IP must be different, because we cannot have 2 same port numbers open.
Right, but there are 2 scenarios, right? So one scenario is it comes from the same machine. So if they come from the same machine, then you know that these port numbers will be different.
Yeah.
The other scenario is that these are the same, in which case you know these have to come from different machines. Yeah. Right? But we can't really take advantage of that. That's why we have to use both of those pieces of information. Because remember, what's happening is when we go out the router, right, we have to be able to go backwards.
Yeah.
So what do we translate it to? I mean, you're right, we could just choose, we have to specify a particular destination and port, but we would in fact, so we have to specify a particular destination and port. We have to specify a particular source, which has to be this IP address. So we've got, of the 4 pieces of of the 4 things we can change, right? Put up 5 fingers. Of the 4 things we can change, 3 of them are fixed. We can't, for things to work, we can't muck with them. So the only thing left that we can play with is, in fact, the port number that this guy, the source port number from this guy. Okay. There was a question at the back first.
So there's a finite number of possible port numbers.
Correct.
That's 65,000.
1,536, yep.
So you're a service provider, and
Sorry?
let's say you're an ISP and you're natting a bunch of your customers together.
Yep.
So you have 10 million customers behind a NAT. Won't your router run out of ports? What happens then?
You're probably right. I'm not exactly sure how I know you can kind of cascade this stuff to a certain extent, but I'd have to think more about what they do. You mean like, for example, like in the one that I had up there where Tokyo had like 10 million or 4 million things, right? There's 65,000 of them. Right? So perhaps then you're going to have to start changing some of the other stuff. So.
I mean, at some point, even if you have nested NATs, you're going to run out of ports.
Oh yes, that's right. You will definitely run out at some point. But if we sort of back off a little bit and say, so what you're actually doing is you're raising the point that many of the people who were involved with the design of the internet say this is why you shouldn't do natting, because it doesn't really solve the problem. All it does is postpone the problem. And in attempting to solve the problem, what you have to do is you have to muck around with 2 layers of the protocol. You have to muck around you have to examine both the network and the transport layer, and then you have to make changes to them and rewrite them. And that seems like that's fundamentally violates this notion of layering and stuff like that the whole thing is built on. And so that group says you should never do natting, and you should move to IPv6. right? So that's the one group. And then there's the other group that says, but it works. It's pretty hard to argue, right? I mean, it works. Yes, it does. And so the other thing would be, well, what about your home network? Right? And something like that. This seemed like a fairly... The problems are different for a home network where you're only maybe got 10 machines, 15 machines, and you can actually have 65,000 connections going out. Right? So that's 6,500 connections at a time from every one of those devices. Pretty unlikely. So you can sort of say for smaller networks, there's a good argument that can be made as a way of sort of saving IP address space and stuff like that. But as you get bigger, it's not clear how much you win.
Good question. In this table, so if there was a source, everything the same, if the source was D and the source port was 86, that would not be okay.
Source here?
Yeah, let's say it was D.
D.
And the port was 86. Now, it should be able to tell that it's different, but that's not okay because source port is really important.
Well, that's why when this one comes along, we have to give it a different outgoing router or a different port number on the outside.
So that entry is totally fine.
This one's totally fine.
Yeah.
This one is the one that's problematic. So we can't just propagate 86 through, like you said. So we have to change it on the other side. So we want to do as little work as we don't want to just arbitrarily, put a different port number out there. We only want to do the work when we have to. We're kind of inherently lazy. So it's only when we sort of get a port collision like that that we would need to do that.
So the router's port number is never the same. In the table, they can't be two, but the same, ever.
I'm thinking carefully. I think that's right. Yeah. So, there was someone else had a question or a comment? Yep.
Can a port be more than 16 bits?
No, ports can't be more than 16 bits. They can't be more than 16 bits because if we look at the actual protocol, the protocol header is not actually a fixed size, but it's close to being a fixed size. There's a one variable field in it, but everything else is fixed and well defined, and they've reserved 16 bits for it. So that's part of the reason why IPv4 is problematic, because they can't, if they could extend things like that, they could also extend the IP address numbers and things. So, okay, yep.
Why do you say that the packet is going from router to router? Like,
sorry?
Why do you label them as R to R versus is it R to or is it R to A?
This one here?
No, R.
Okay, because I'm saying that when we look at this packet that's going out on the network, it has to appear to have come from some place that you can get back to.
Oh, but is it R or A? Oh, A, okay. I see it.
Is that an A
Oh,
or R? You can see your R as an A.
okay, so the destination is A, the source is R. Oh, I see, okay. You don't want to read my real writing. Okay, so the question, so given what I said here is, and the question that was raised earlier, there's another issue that says, well, how long do you keep these? Because if you keep them indefinitely, right, suppose that your connection to the other side, you stop using it, right, but you've still got the entry in there, because you never know when something might come from the other side. So that means that if someone else comes along, you have to add more entries and stuff like that. So there are a couple of strategies. So a standard strategy is just to have time-based. And you just sort of say, when was the last time I had to use this rule, either going in or out? Okay? And if it's been more than 5 minutes, 10 minutes, whatever your magic number is, then you erase the rule. And you may have actually experienced this at home. Because what will happen is, depending upon how you have things set up, you might do an SSH into the university, and then you come back 2 hours, do nothing, come back 2 hours later, and it says something like connection closed or something like that, right? Well, what has happened is that, so it turns out that for most connections, when you make a connection from, say, C to A, if you don't use it, there's no traffic on there. They actually don't send any data. So you send some data initially, and then they stop. Okay, if they don't send anything, so there's no way to know whether or not either end has died. Okay, so that's essentially what's happened in your particular case, is they've timed that rule out. You can get around that. On most SSHs, there's a minus timeout thing that you can put on there or something like that. Or actually, they typically call it keep alive. So some sort of keep alive, and if you set that like at 2 or 3 minutes, then every 2 or 3 minutes, it'll just send a little packet along. And that's enough to tickle the rule and keep it alive. Okay? So now what's going to happen, right, is all you people who didn't know about the rule will be looking that up, and we'll see tons of connections being left open on machines for days at a time and stuff like that, right, from your home. So that's one. Another one is a little more clever. Okay? It actually turns out that something that we haven't talked about, but when you make a connection, there's actually a packet goes out that's called, I want to say snack, but that's not right. I'm thinking of I know off the top of my head, I can remember the names for the other ones. I can't remember the initial ones. Because there's some initial ones that go out that basically say, I want to talk to you. Okay, and then the other side comes back and says, yes, I'm willing to talk to you. Okay, so that's how you know whether or not, for example, when you go to a machine and you make a connection quote to a web server, if there's no web server there, what happens is you sent a connection request out, and what happened was something came back and said, nope, nothing there. I'm not willing to accept that. Okay, so it also turns out that when you stop using a connection, by stop using, I mean like the program ends, or you do a close like you do in your assignments, there's actually called a fin packet goes out, which means finish. Okay, so what you do is, if you're a little smarter, is what you do is you watch for the fin packet to go out. Okay, so so now this is even getting more complicated, because now what do you have to do? It turns out that the bits that indicate a packet is a fin packet are more transport level stuff. So you have to watch the transport level stuff for the fin packet to go out. And you come back, and you have to also watch for the acknowledgement to come back. Both sides have to agree that it's ended. And once they both agreed that it's ended, then you know that nothing more will be going out that way, and so you can get rid of it. Get rid of that translation.
So that reads the protocol running at the transport layer?
Yeah. So when you looked in Wireshark, say in like, right, I don't know if you ever, did you see any of the ACK ones? Okay, so when you see the packets that were marked ACK, those are, the Wireshark is actually inspecting the transport layer and looking at the field that says this is an ACK packet. And you saw other ones that would have said they were data packets, right? So they get marked that way, and it looks at them and you can tell. And so the router is essentially having to do the same sort of thing. It's having to distinguish between those different types of packets and work with them.
Doesn't that mean that a router is actually not stopping at the network layer?
That's exactly what it means. It means the router's not stopping at the network layer and it's going up, which again harkens back to the argument that says routers should only look at the network layer. They shouldn't be looking at these other things. And once they're doing that, they're not routers anymore. They're other things, and they're more complicated, and so that sort of breaks our layering model and stuff like that. So the whole idea, so it gets worse than that. Okay. I'll have a scenario on, it's Wednesday we meet next, right? Because Monday's a holiday. And there's a scenario where it actually turns out you have to even look up into the application layer when you start doing stuff like this. So it gets even worse. And so stuff like that is referred to as deep packet inspection and things like that. But
so getting rid of the entries so we can reuse the router port numbers, there's two strategies.
Time, yeah.
And the fin packet.
Yeah, watching them.
Watching them, then you turn that in.
Yeah. Okay, just a second. Okay, so before you guys go, have a nice Thanksgiving. See you Wednesday. Yes, that's.
Right.
I like the first song. I'm back to the last song.
Hi. Who are you? How are you doing, man? I'm doing speech these days. It's good for a certain
It's like the.
Yeah, no, 110.
Same stuff.
Almost got to go by. Almost. No.
But they needed you to get everything.
Yes, I was originally assigned to 10 and then.
I think it has to take a second.
I'll say it. I come through.
There was a minor.
Tell me what your feelings.
Or whatever it's on.
That I learned about sex.
There probably won't be any virtual reality.
What were you dancing like? Like satisfaction.
Okay, check this out. There was a recent guy. This pair. Round two, random years.
For the writer, because the writer.
3 hours.
Guys, the guy said, yeah, I'll go on a date. 95% said, yeah, I'll have sex with you right now. 50% said, yeah, I'll go on a date. 20% said, yeah, I'll have sex with you.
We joined the
They talk about why it